The B-52 Stratofortress has been flying since 1952, and now it's getting the most significant upgrade in its history. The Air Force is replacing all 8 engines on its entire B-52 fleet with Rolls-Royce F130 turbofans. And this isn't just about keeping an old bomber in the air. This re-engineering program is setting precedents that will reshape how the entire aviation industry thinks about aircraft longevity, sustainability, and lifecycle management. The implications stretch far beyond military applications, touching commercial aviation, engine manufacturing, and the future of flight itself. What makes this upgrade so revolutionary isn't just the technology, but what it proves is possible. The B-52's current TF-33 engines date back to the 1960s. They're fuel-hungry, maintenance-intensive, and increasingly difficult to support as parts become scarce. Each B-52 burns through fuel at an alarming rate, limiting its range and operational flexibility. The engines require constant attention, with maintenance crews spending countless hours on upkeep that takes aircraft out of service. But here's what's remarkable. The airframe itself remains structurally sound. The B-52's robust design means the fuselage, wings, and basic structure can fly for decades more. This created an unusual situation where the platform's potential far exceeds its propulsion system's capabilities. The Air Force faced a choice: retire the fleet early or invest in modernization. They chose modernization, but not just as a band-aid solution. The new F130 engines will transform the B-52 into essentially a new aircraft. These engines deliver 30% better fuel efficiency, eliminating the need for aerial refueling on many missions. They're quieter, cleaner, and require significantly less maintenance. The reduction in support requirements means more aircraft available for missions and lower lifecycle costs. Perhaps most importantly, Rolls-Royce's F130 is based on their BR700 family, engines currently flying on commercial aircraft worldwide, ensuring parts availability and support for decades to come. But the decision to re-engine rather than replace reveals something the industry is just beginning to understand about the true economics of aviation. The F130 isn't a clean-sheet military engine design. It's derived from the BR725, which powers business jets like the Gulfstream G650. This commercial heritage is precisely what makes it revolutionary for military aviation. The engine incorporates decades of commercial aviation advances, advanced materials, digital engine controls, and health monitoring systems that weren't imaginable when the B-52 first flew. The core technology provides 17,000 pounds of thrust per engine, while maintaining exceptional fuel efficiency through high bypass ratio design. Unlike the old TF-33s, which were essentially turbojets with minimal bypass, the F130 is a modern high-bypass turbofan that routes most air around the combustion core. The digital engine control system represents a quantum leap. Each engine continuously monitors itself, tracking performance parameters, predicting maintenance needs, and optimizing fuel consumption in real time. This isn't just convenient, it fundamentally changes aircraft operations. Ground crews receive diagnostic data before landing, enabling proactive maintenance instead of reactive repairs. The system can detect anomalies that human operators might miss until they become a serious problem. Integration with the B-52's modernized avionics creates a fully networked propulsion system where all 8 engines communicate with each other and the flight deck. Material science advances are equally crucial. The F130 uses single crystal turbine blades that withstand higher temperatures and stresses than anything available in the 1960s. Composite fan blades reduce weight while improving durability. Ceramic coatings protect hot section components, extending service life. These materials allow the engine to operate more efficiently while requiring less frequent overhauls. The maintenance intervals are measured in years rather than months, and the engines are designed for on-wing maintenance wherever possible, reducing the need to remove engines for service. What's fascinating is how this commercial-derived engine is proving superior to purpose-built military designs in almost every metric that matters. The B-52 re-engineering program costs approximately $2.6 billion for 608 engines across 76 aircraft. That's roughly $34 million per aircraft, which sounds expensive until you compare it to alternatives. A new strategic bomber costs over $600 million per aircraft, making the B-52 upgrade roughly 6% of replacement cost. But the economics go deeper than initial investment. The fuel savings alone are staggering. The Air Force estimates the F-130s will save $2 billion in fuel costs over the fleet's remaining service life. With 30% better fuel efficiency, each aircraft can fly longer missions without refueling, reducing operational costs and increasing mission flexibility. Maintenance economics tell an even more compelling story. The TF-33 engines require intensive maintenance with specialized tools and personnel. Many components are no longer in production, forcing the Air Force to maintain aging supply chains or cannibalize retired aircraft for parts. The F130s eliminate these problems entirely. Because they're based on commercial engines, parts are readily available through established supply chains. Maintenance procedures are standardized and well documented. Training is easier because many technicians already have experience with the BR700 family. The engines themselves require fewer shop visits and less hands-on maintenance. The Air Force projects maintenance costs will drop significantly, with more aircraft available for missions because fewer are in maintenance. This economic model is making other military services and commercial operators reconsider their assumptions. Why buy new aircraft when upgrading existing platforms delivers most of the capability at a fraction of the cost? Airlines are watching closely because their fleets face similar questions. Aircraft like the Boeing 777 or Airbus A330 have excellent airframes, but aging engines. Could selective re-engining extend their service lives while improving efficiency? The B-52 program is proving that sometimes the most economical solution isn't the newest aircraft, but the smartest upgrade. Military aviation typically doesn't prioritize environmental concerns, but the B-52 re-engining program delivers substantial environmental benefits anyway. The F130 engines reduce fuel consumption by 30%, which directly translates to 30% fewer carbon emissions. They're also significantly quieter than the old TF-33s, reducing noise pollution around air bases. Lower emissions aren't just about environmental responsibility, they affect operational capabilities. Reduced fuel consumption means smaller logistical footprint. Less fuel to transport means fewer tanker trucks, less vulnerability to supply chain disruption, and reduced dependence on forward fuel infrastructure. In contested environments, logistics is vulnerability. The ability to operate with less support makes the B-52 more strategically flexible. The strategic implications extend beyond individual missions. Reduced refueling requirements mean fewer tanker aircraft needed for bomber operations. Tankers are valuable assets with multiple demands on their availability. Freeing up tanker capacity allows them to support other aircraft or missions. The extended range also changes strategic planning. B-52s can now reach targets that previously required multiple refuelings, some of which might have been in politically sensitive locations. Reducing refueling needs provides more direct flight paths and less exposure to potential threats. The ability to loiter longer on station increases mission flexibility and response options. But there's a larger strategic lesson here about sustainability in military operations. The U.S. military is the world's largest consumer of petroleum, and fuel costs represent a significant portion of defense budgets. Any technology that reduces fuel consumption without sacrificing capability is strategically valuable. The B-52 proves that environmental efficiency and military effectiveness aren't contradictory. They can reinforce each other, creating aircraft that are both more capable and more sustainable. This realization is starting to influence how military planners think about future aircraft acquisitions and the role efficiency plays in combat effectiveness. The commercial aviation industry is watching the B-52 program with intense interest because it challenges fundamental assumptions about aircraft economics. Airlines typically retire aircraft after 20 to 30 years, not because the airframes are worn out, but because newer aircraft offer better economics. But what if selective upgrades could deliver similar economic benefits at much lower cost? The B-52 program suggests this is possible. By replacing just the engines while retaining the airframe in most systems, the Air Force achieves most of the benefits of a new aircraft for a fraction of the cost. The model is particularly relevant as aviation faces pressure to reduce emissions while managing costs. Several airlines are already exploring re-engining programs for existing aircraft. The concept isn't entirely new. Boeing's 737 MAX is essentially a re-engined 737, and Airbus did the same with the A320neo family. But those were manufacturer-led programs on relatively young designs. The B-52 demonstrates that even much older aircraft can be economically and technically viable for re-engining. The key is matching the right engine to the right airframe and ensuring the structural and systems integration works properly. Boeing and Airbus have studied re-engining options for aircraft, like the 777 and A330. but concerns about development costs and market demand have prevented programs from launching. The B-52's success could change this calculus. It demonstrates that the technical challenges are manageable and the economic benefits are substantial. For airlines operating fleets of paid-off aircraft, re-engining could extend service life while dramatically improving fuel efficiency. This is particularly relevant for cargo operators and charter airlines flying older aircraft, where purchase prices are low but operating costs are high. The environmental benefits provide additional incentive as regulations tighten. Aircraft that can meet future emission standards through engine upgrades avoid premature retirement. The fundamental question the B-52 poses to commercial aviation is whether the industry has been retiring aircraft too early, discarding value that could be captured through strategic upgrades. Rolls-Royce's F130 win is more than just a lucrative contract. It's validation of a business strategy that could reshape the engine market. By adapting an existing commercial engine rather than developing a new military-specific design, Rolls-Royce reduced development costs, accelerated timelines, and created economies of scale that benefit both military and commercial customers. The BR700 family now has military credibility, potentially opening doors to other defense applications. This approach contrasts with traditional military engine development, which typically starts from scratch with unique requirements, resulting in expensive, specialized engines with limited production runs and high lifecycle costs. For competing engine manufacturers, the B-52 program is a wake-up call. GE and Pratt & Whitney have traditionally dominated military engine contracts with purpose-built designs. Rolls-Royce's commercial-to-military pathway suggests an alternative approach that may be more attractive to budget-conscious military buyers. This could influence future competition for engine contracts across multiple aircraft types. The commercial foundation also provides sustainability advantages. Parts commonality, established supply chains, and commercial maintenance infrastructure reduce lifecycle costs while improving availability. These factors increasingly matter to military customers managing aging fleets with constrained budgets. The program also demonstrates the value of maintaining diverse engine platforms. Rolls-Royce's BR700 family now spans business jets, potential commercial wide-body applications, and strategic bombers. This diversity strengthens the business case for continued investment in the platform, ensuring it remains technologically current. Each application feeds the others, creating a virtuous cycle of development and improvement. Military reliability requirements drive enhancements that benefit commercial operators, while commercial volume provides economic foundation for the platform. For the broader engine industry, the B-52 program signals that the future may favor adaptable, scalable engine families over bespoke designs, fundamentally changing how manufacturers approach new development. The B-52 re-engining program establishes precedents that will influence aircraft lifecycle management across military and commercial aviation. It demonstrates that aircraft lifespans aren't limited by airframe age, but by economic and technical viability of keeping systems current. The B-52 will fly with engines designed in the 2020s on an airframe from the 1950s, a 70-year technology gap that would have seemed impossible a generation ago. This proves that with proper structural maintenance and strategic upgrades, aircraft can remain relevant far longer than traditionally assumed. The implications are profound for how operators think about fleet management and capital allocation. The program also validates a modular approach to aircraft modernization. Rather than comprehensive overhauls that update everything simultaneously, selective upgrades targeting the highest impact systems can deliver most of the benefits at a fraction of the cost. The B-52 is also receiving avionics upgrades, communications improvements, and weapons system enhancements, but these are separate programs that can proceed independently of the engine replacement. This modular strategy allows spreading costs over time while keeping aircraft operational. It also reduces risk by breaking massive programs into manageable pieces with clear objectives and measurable benefits. For military services worldwide, the B-52 provides a roadmap for managing aging aircraft fleets. Many countries operate aircraft designs from the 1970s and 1980s that remain structurally sound but lag technologically. The traditional response has been procurement of new aircraft, which is expensive and often delayed by budget constraints. The B-52 model suggests an alternative: strategic upgrades that keep existing aircraft relevant while deferring or reducing new aircraft purchases. This is particularly attractive as new aircraft costs have skyrocketed while defense budgets face pressure. What's emerging is a new paradigm where aircraft lifecycle management becomes more like ship maintenance, with platforms continuously updated and modernized rather than replaced wholesale after a fixed period. The B-52 engine program is transforming defense industrial practices in ways that extend beyond aviation. Traditional military procurement emphasizes unique, specialized equipment with dedicated supply chains. The F130 takes the opposite approach, leveraging commercial supply chains, commercial manufacturing processes, and commercial support infrastructure. This reduces costs while improving sustainability and responsiveness. Rolls-Royce manufactures F130 engines on the same lines that produce commercial BR700 variants, using the same suppliers, quality systems, and support networks. This integration creates efficiencies impossible with dedicated military production line. The supply chain implications are substantial. Military aviation has historically struggled with parts availability as aircraft age and production lines close. Components become obsolete, suppliers exit the market, and maintenance becomes increasingly difficult and expensive. The F130 avoids these problems by tying into active commercial supply chains that will remain viable for decades. When an F130 component needs replacement, it comes from the same suppliers supporting commercial aircraft worldwide. This ensures availability, competitive pricing, and continuous improvement as suppliers enhance products for their commercial customers. This model is influencing other defense programs. The U.S. Air Force's re-engining program for the KC-135 tanker similarly uses commercial engines. Other services are evaluating commercial solutions for traditionally military-specific requirements. The shift represents fundamental thinking about defense acquisition, emphasizing sustainability and lifecycle costs rather than just initial capability. It also reflects maturity in commercial technology. Today's commercial aircraft engines often exceed military-specific engines in reliability, efficiency, and performance, eliminating the technical case for unique military designs in many applications. The broader industrial impact includes workforce development, as technicians trained on commercial engines can transition to military maintenance and vice versa, creating more flexible and capable maintenance organizations. The F130 engines bring digital sophistication that transforms B-52 operations, but they also preview the future of aircraft systems integration. Each engine is essentially a network node, continuously communicating with other engines, the flight deck, and ground stations. Data flows in real time, enabling optimization impossible with older mechanical or analog systems. The engines can adjust thrust automatically to optimize fuel consumption based on mission parameters, weather, and aircraft weight. They can compensate for individual engine variations, ensuring all 8 engines work in perfect harmony. This level of integration requires sophisticated software and network architecture that represents the future of aircraft systems. The digital architecture also enables predictive maintenance that fundamentally changes operational planning. Instead of scheduled maintenance based on flight hours or calendar time, maintenance occurs based on actual condition and predicted remaining life. Sensors monitor engine health continuously, tracking wear patterns, performance degradation, and component stress. Machine learning algorithms analyze this data, predicting when components will need replacement before failures occur. Ground crews receive advance notice of maintenance requirements, allowing scheduling that minimizes operational impact. This predictive approach increases aircraft availability while reducing unnecessary maintenance on components still in good condition. But the most significant implication is how this digital integration model scales to entire aircraft and entire fleets. The B-52's engine network is a microcosm of future aircraft, where every system connects, communicates, and optimizes. Future aircraft won't just have digital engines. They'll be digital platforms where propulsion, avionics, weapons, communications, and support systems form integrated networks. This enables capabilities impossible with standalone systems. Automatic optimization, distributed processing, enhanced redundancy, and fleet-wide learning where insights from one aircraft improve all others. The B-52, ironically one of aviation's oldest designs, is becoming a testbed for operational concepts that will define how next-generation aircraft function and fundamentally alter what we consider an aircraft to be. The B-52 re-engining program's influence extends far beyond a single aircraft type or even military aviation. It's changing fundamental assumptions assumptions about aircraft lifecycle economics, technology integration, and the relationship between new and existing platforms. Airlines are re-evaluating retirement decisions for older aircraft, considering whether upgrades could extend service life profitably. Manufacturers are reconsidering new aircraft development timelines and costs, wondering if the market will accept evolutionary upgrades over revolutionary new design. Regulators are grappling with how to certify major modifications to existing aircraft types, balancing safety with the economic and environmental benefits of keeping good airframes flying. The program also influences international aviation. Many countries operate aging military fleets they cannot afford to replace wholesale. The B-52 model offers an alternative path: strategic upgrades that modernize capabilities without new aircraft procurement costs. This is particularly relevant for middle-power nations where defense budgets are constrained but security requirements remain pressing. Several countries have expressed interest in similar programs for their own fleets, from transport aircraft to fighters. The approach also applies to commercial aviation in developing markets where airlines operate older aircraft but need improved efficiency to remain competitive. Perhaps most significantly, the B-52 program is changing how we think about technological progress in aviation. The industry has long assumed progress requires new platforms, that achieving better performance demands new aircraft. The B-52 challenges this assumption, demonstrating that smart integration of new technology with proven platforms can deliver most of the benefits at a fraction of the cost. This doesn't mean new aircraft development will stop, but it does suggest a more balanced approach where upgrades and new builds both play roles in fleet evolution. The question now facing the entire aviation industry is how many other B-52 opportunities exist, aircraft that could be transformed through selective upgrades rather than retired and replaced. The B-52 re-engining program represents more than modernizing an old bomber. It's a proof of concept for aircraft lifecycle management that prioritizes sustainability, economic efficiency, and technological integration. The lessons learned apply across aviation, from military strategic platforms to commercial airliners. As the first re-engined B-52 seconds enter service, the industry will be watching closely to validate the performance, economics, and operational benefits. The success of this program will influence aircraft modernization decisions for decades. If you found this analysis valuable, explore our other content on aviation technology and defense innovation.